Thanks, Anshul, for that introduction, and good afternoon, everyone. Uh, I hope you have settled down after lunch. If not, then definitely after my talk. And today, what we are going to be talking about is the shuffling problem in data processing, but more focused on uh, shuffling for a heterogeneous workload where you have to do some processing on CPUs, shove the data for training on GPUs. So that opens a very interesting set of challenges. But before that, I quickly want to uh, introduce the Ray project, like in the slide title, as you see here, Ray Exoshuffle, which um, is part of a very healthy, growing open source project. Um, and Basically, this Ray project has been there since 2016, but it took off in a phenomenal way after Gen AI boom. And what this project helps you with is parallelize any kind of Pythonic application, but its suitability for AI ML workloads, especially in the LLM era, is where this project became hugely popular, and we have so many thousands plus contributors and a lot of Ray clusters being launched globally. All in all, it's an AI compute engine. So there is a core orchestration layer, and it exposes some core primitives using which you can distribute any kind of workload, not just AI ML. You can build a simple data processing system on top of Ray core as well. And indeed, those Ray AI libraries is one of the popular data processing systems. Train is used for training, tune for tuning, serve for inference, RLlib for reinforcement learning, and post training. So all those AI libraries make use of this core layer. And the shuffle problem that I'm going to be talking about, that basically leverages the primitives of core to solve that problem. But let's first understand what is shuffle. Forget about GPUs, forget about large scale data processing. In general, this shuffle problem is something like this. Usually, when you are processing big data sets, you would not process everything in one go. You would partition them into some chunks, and you divide your data processing into stages. Maybe so typically this parallel processing, massive parallel processing terminology, MapReduce, was made popular by Google, but reduction, mapping, all these concepts as mathematical constructs have existed since forever. So what happens in Shuffle is that you do some work in a particular stage. Each of these boxes, think of them as workers who are processing some split of data, some stage. And then once you are done with that stage, the workers need to ship the data. The process data of stage one needs to be shipped to stage two, right? So this redistributing data between computation stages. So each worker gets the right partition so that they can do their job. Could be grouping by some key, a very popular operation. That's all that shuffling problem is. It sounds very simple, but when you start doing this at a large scale, at hundreds of terabytes, petabyte scale, problems emerge. And when we get to the machine learning world, where you need to shuffle data before feeding it to GPUs, different kinds of challenges emerge, as we'll see. Um, So what happens in machine learning training? Quick show of hands, ML engineers here who have done small scale, large scale, doesn't matter, but have done training, right? Very few. Okay. You would surely be able to relate to this, but these are simple operating systems concepts. Uh, so ML training, the unique thing about ML training is that it requires to repeatedly shuffle the training data set between epochs, because you want you don't want to induce bias by a certain order of data. You don't you want your higher training accuracy. So you need to do this very often. And the shuffle systems that exist, most of the shuffle systems that are provided by data processing systems like Apache Spark, those are global in nature. In the sense, you need to have this the data shuffle stage, which is CPU intensive, uh, run synchronously, and after that whole shuffle step has completed, only then you can feed the data to the GPU intensive training phase. All this while, what happens is your GPU for certain amount of time is just sitting idle, which leads to underutilization of GPU, and GPUs are costly. Not only that, your overall training time, so the whole training time between each epoch is increasing, and you're doing this for multiple epochs for better accuracy, right? So uh, operating systems 101 basically teaches that what if we can simply pipeline this? Why do I have to keep my GPUs idle for so long, right? If some portion of my data here is ready, why don't I ship this here and let the training begin? Okay, that's the fundamental concept behind exoshuffle, and we'll talk about that. That there is programmability and extensibility angle to it as well. But fundamentally, if from the next 25 minutes, anything I want you to take away is the problem that is getting solved was that, right? But before that, quick history. What were the popular shuffle algorithms? Uh, so those who already know this can just Google for this paper, Exo Shuffle paper. And if you're interested, you can read more details in that paper. My talk is basically based on that, which we did in Ray project. So MapReduce, it started with pull-based shuffle. What that means, basically, you have, let's say, M mappers are reducers, and you can, so these are M times R intermediate blocks that go over the network. And you can imagine once you have to, let's say, aggregate terabytes of data, these are millions of tiny blocks. So a lot of, you would hit disk IOPS limit. And of course, network, you would saturate as well. So people got a little bit clever here. What they did is, why to transfer so many tiny small blocks? What I'll do is maybe merge some of the map outputs and transfer only the merged blocks. So those merged blocks did help, of course, but even this merging step used to happen before the reduce phase, before the network transfer. So reducers were still waiting for data, right? Then came the push-based shuffle, and this was developed independently at different companies, LinkedIn, Uber, all these companies were independently working on it, which is a neat trick, basically, that let's push the merge phase to the reducer side. Network bandwidth is not a huge limitation for us. What we can do is, if we push this merge phase to the reduce side, then we can pipeline certain map outputs as and when they are ready. Let's ship it to merge phase, and we can pipeline this map and merge, and have better utilization of the resources. So that was the idea, and it's a genuinely good optimization, and it exists today as well. This is very recent though. Spark 3.2, I think it released sometime back in 2023 or so. So very recent. And what's the problem here? So all these great algorithms, but what's the problem? The problem is all of this come bundled with their own coordination and orchestration systems. So these are essentially locked in, packaged in one tight system. These are not extensible. It's not as if you can swap them as libraries, have the same data plane, but swap them as libraries. That's not possible today with anything. You pick any data processing system today. So that's what Ray changed. But before that, a quick intro to Ray internals. So Ray cluster looks something like this. How many here have actually worked with Apache Spark? Okay, so quite a few. Good. Then you'd be able to relate to Spark cluster is no different. And in general, parallel processing systems, they have this kind of architecture. You have in Spark, you can call it driver. In things like Presto Trino, you call it coordinator. In Ray, you call it head node, for the lack of better name. And then there are worker nodes. Um, the difference from something like Spark is this middle box, the raylet that you see on each and every node. So in case of Spark, all the planning happens on the driver, and then executors are basically stateless, right? You just tell them, hey, this is the plan, and this is how my data is laid out. Go ahead and execute it. In case of Ray cluster, Raylet kind of acts as a distributed scheduler. It's not just the head node which is doing the scheduling, but even worker nodes can schedule some tasks. And the Raylet also manages the memory on that node. So any output produced by any worker node can live on any node, not just that node. In Spark, if you were to shuffle and you are exceeding memory limits, then you would write to the disk. Well, there are projects today, Apache Caliborn, and there is one more, I think, from Alibaba, Unifil, which provide remote shuffle services. But those were not there a couple of years ago. And yeah, even then, there are problems with that. When it comes to ML training workloads, they work perfectly fine for traditional ETL data processing workloads. So this Raylet component of Ray cluster is very, very important. It acts as a distributed scheduler and distributed shared memory for the whole of Ray cluster. And then there is a GCS component at the second last blue box, GCS. It's like manages the control plane. It has complete cluster resource view. Then certain auto scaling components, that's fine. That's not important for our discussion today. Typically in production, you wouldn't run worker process on head node, but you can. There is nothing restricting you, but you shouldn't. Okay, so that's what a Ray cluster looks like. Only thing to take away from this diagram is that Raylet box, okay, which differentiate it from something like Spark. The other thing that I want to mention here is Ray also exposes certain APIs, which makes it very easy to distribute your workload. So ray.remote, ray.wait, and get are all those APIs. In simplest terms, if I have to explain this is basically futures in Java or any other programming languages with any async primitives that they provide. This basically that, but distributed. So distributed futures comes with its own sort of challenges. So remote API is used to submit the tasks, and it returns you a handle. Wait you can use to synchronize across tasks if needed, and get, if you invoke a get on a handle, it will basically start fetching the result. So just these three APIs lets you do a lot of things, and we'll see a code snippet later on. All right. So now, what is ExoShuffle? With that overview of Ray cluster and the APIs that it exposes in mind, let's understand ExoShuffle. Before that, maybe I will just quickly show you this diagram here, that data processing framework diagram. And I mentioned that all these great algorithms, shuffle algorithms, bundled in one tight system, each with its own data plane. So Ray basically says that, you know what, that data plane part where you need to, which needs to be fault tolerant, which takes care of lineage reconstruction, all those things you don't need to do it separately for different kinds of shuffle algorithms, right? So let just build it once, let it be there, and then expose all these different shuffle strategies as libraries, or in case of ray, it's basically uh, simple a config switch. But between that, so data plane is that reliable fault tolerant layer which takes care of doing the lineage reconstruction, or any actually executing the shuffle. So the worker node sit there, but and then on top of that, it's distributed futures API, those remote wait or get APIs, this thin distributed futures API. And on top of that are these shuffle strategies, where any data processing or ML training workload can configure what kind of shuffle they want to run. What these distributed futures give you is they return you a handle, right? So you can have you can continue doing whatever you want to do next, and let your data your data could be located anywhere, not necessarily on that node, and everything is taken care of by the raylet sitting on that node. So raylet, and we'll see next. I'll explain how this looks like in action. So what happens here is, so I'm comparing Spark and Ray data, how they execute shuffle. But let's just focus on Ray data. Once you understand Ray data, and then you can easily compare it to Spark. What basically happens is you have these data partitions coming on the left, and depending on the node, you have, let's say, 3 CPUs, 2 GPUs. You start putting in some partitions there. Some couple of CPUs complete fast enough, and in here you'll see blocks 1 and 2 are immediately available in Ray object store, and then the GPUs start consuming from there itself. They don't have to wait for all the 4 partition blocks to produce their output in object store to for GPUs to start consuming. So that object store creates a big difference as compared to Spark. Um, that object store enables pipelined I/O, which kind of hides the latency of training that we originally talked about. GPUs were sitting idle. So in this case with Ray, GPUs never sit idle. But there is a question about fault tolerance for sure. You know what? Now your buffer is here with the node. What happens when one of my CPU or GPU just the worker crashes? So this object store itself is managed by a separate process. It does not interfere with the worker processes. But then you can again ask, oh, what if the node itself goes down, right? Then of course, in case of hardware failure or for whatever reason, the node is down, you are working in a spot environment, you have been preempted. Even there, Ray attempts to differentiate between system and application errors. So if it's a preemption case, it will try to drain the work that is being done. It's a best effort basis, which does not happen today in Spark. There are plugins for Spark that can do so. Spark does expose listeners, so you have to write your own thing. In case of Ray, you get it out of the box. So yeah, the head node, if the head node is living, then even then, with the transparent disk spilling from the object store to the disk or to the cloud, head node knows where some particular partition of data after having been processed lives, and it will, once again, whenever the worker or the node comes up, it will make sure that things are checkpointed, so that things start moving from the last checkpoint onwards in an incremental manner. So coming back to the code, this is what looks like a simple shuffle, pull based shuffle, where you have m times r intermediate blocks, inefficient shuffle, let's just call that. So you have m mappers, r reducers. Once you do map.remote, and it immediately starts submitting m tasks. And you don't really have to wait for. So what this map output contain is a list of handles. So you can do ray.get reduce.remote map out. Now you are invoking reduce task on different elements of the map out. And this does not necessarily have to have the data that those handles are going to produce ready. Internally, Ray ensures it, because of the resource view and the object level metadata that Ray has, it knows what workers are processing what parts, and as and when they get ready, it will fetch it for you. This is the push based or the efficient shuffle. That also kind of code very simple. I won't go into explaining each and every line, but the point that I want to show here is if you go and look into the implementation of Spark, push based shuffle implementation in Spark, and that's quite bulky. Few hundred, lower thousand lines of code, and that too, it's not easily swappable by another shuffle strategy. In Ray, it's just as simple as this. Of course, Ray data behind the scene is hiding a lot of implementation of stuff, but the core mapper reducer loop, that's still less than 100 lines of code using pure Ray core primitives. And when I say Ray core primitives, it's basically tasks and objects using these remote wait and get APIs. So yeah, we talked about the system design, and we talked about the usability point of view as well. But then how does it perform on a real workload? So ML engineers might be familiar with this, but I wanted to show two kinds of benchmarks here. The first, of course, is pertaining to the ML training itself, the whole hypothesis of this talk, what actually happens on a real workload, training workload. So this is distributed training of a TabNet model on Higgs dataset. For those not familiar with it, just think of a simple classification problem, okay? And the baseline here that we are comparing, PyTorch is a very popular library. I mean, even non-ML folks would have heard about PyTorch for deep learning, not just deep learning, but in general, any machine learning training, machine learning work task that you want to perform. But even more popular in the deep learning world. And Petastorm is a library which helps with data loading. For the purpose of this benchmark, that's all we want to know. Petastorm is a very popular library which was developed at Uber. And so PyTorch plus Petastorm, the training time. So x-axis is basically the training time, y-axis is the accuracy. Because of that synchronous shuffle, this took longer time. While with Exo Shuffle, because we can pipeline the partially shuffled outputs to the GPU, it takes much less time. But also, it converges to the higher accuracy much faster, right? To achieve the same accuracy with PyTorch plus Petastorm, you would have to go much further in time axis. I just cut it short here. So that's the beauty of that architecture for training workloads. But that does not mean you have to compromise scale. The scale of data here was not big. Okay, the problem here was that GPUs were just sitting idle, and overall training time was huge. Here, the scale of data is big. Well, it's a very popular, CloudSort is a very popular benchmark, public benchmark. And currently Ray holds the record in terms of price to performance ratio, sorting 100 terabytes of data under less than $1 per TB. That's Ray's record. Previous record was, of course, held by Spark, before that Hadoop. So this benchmark 2 is comparing native Spark without the push-based shuffle. Then Magnet bar is basically Spark with the push-based, the efficient shuffle strategy that I told you. And then Exo Shuffle with the push-based shuffle strategy. So Exo Shuffle, don't think of Exo Shuffle as a new algorithm. Replace any shuffle algorithm within ExoShuffle. So ExoShuffle with push-based shuffle strategy that outperforms even the push-based shuffle on Spark. So the data set consists of this 100 TB. Whenever someone just gives you a complete number, always ask the breakdown, how many partitions, how many nodes. That helps you further understand the benchmark. So these are 50,000 partitions across 100 nodes. You could further ask what type of nodes, and you should always look for the details, which you'll find in that paper. I didn't just put it on the slide yet. So, okay, so the key takeaway from this talk, right, is that it's not comparing data systems per se, even though I ended with benchmarks. The second last slide was benchmark, but it's not comparing data systems. It's more about, look, Spark still, for traditional ETL processing, it's still one of the best processing frameworks out there. But now the world is moving more and more towards feeding things into GPU. Even traditional data processing, there are database engines that are coming which are getting accelerated by GPUs, right? So the near future, it already is in AI native companies, but going to be even more common. Near future, it's going to look like this. You are going to be processing data on both CPUs and GPUs. So it's going to be a mix of heterogeneous resources. And GPUs are costly. You don't want them to be sitting idle while things are running on CPUs. You want this streaming fashion, this pipeline fashion of IO work happening. And that is the main strength of Ray. You don't really have multiple copies of data. That's the second point. In case of Spark, you would end up with multiple copies of data. When you move data from, materialize it after processing on CPU and then move to GPU. Here, that's not an issue in Ray. It's built, Ray core itself is very general purpose, but the complexities are hidden by library sitting on top of it. It's built for, yeah, the third point is basically summarizes it all. It's built for AI workloads running across heterogeneous resources. AI is actually, simplifies it. If I had to say, it builds for high performance HPC systems, basically, high performance computing workloads across heterogeneous resources. Heterogeneity is important here, which will show the advantages of pipelining. And that's all. I'm happy to take any questions if you have. Yeah, I thought so after lunch. Oh, sure. Yeah, go ahead. Can I have a mic here? Okay.
Can I use? Hey, Sagar. Hello. This is for
Who?
yeah,
Oh, there. Okay.
yeah. So training is fine. Like this exo shuffle will help. What about inference? Will it help there also?
Inference, you have to break it down. There are certain steps in inference which are memory intensive, while certain steps which are compute intensive, right?
Yeah.
So, for example, prefill. So inference involves well, I'm generalizing this, but so I'm talking more from a context of LLM inference.
Okay.
Simple inference is much simpler problem. If it's a tabular data and you have nobody is running inference on ResNet model today, right?
Yeah.
Forget tabular data, image models, nobody is running on ResNet today, correct? These are all very high complex models. So when you get to complex models, especially since the transformer architecture era, so after 2017, your prefill step is very memory intensive. Decode step is very compute intensive, right?
Yeah.
So while you have to think about how to schedule the work here. You neither want your compute heavy step, the cores to be empty, but at the same time, you don't want that your cores are uh, doing so much work that memory is not getting emptied fast
Yes.
enough, right? So this is a very careful balance required here. Whether ray data exo shuffle will help or not, uh, not straight away, right away. But there is a library called VLLM, very popular library. Just look for it, right? It's from the same lab that where Ray was developed, and the same lab where Spark was developed. In fact, the same lab where Mesos was developed. The first talk brought up Mesos as well in Berkeley. And so VLLM basically utilizes Ray core primitives to take advantage of the fact that there are compute heavy steps and the memory heavy steps, how to pipeline the work better.
Okay.
Yeah, to answer your question in short, Ray data exo shuffle out of the box, no. Use VLLM. Ray core primitives, they use Ray core primitives. And Ray core primitive is so general purpose that you can do any kind of work, any high performance compute. That's why HPC workload I wanted to gear more towards that, but I mentioned AI workloads to relate to the folks more.
Yes, understood. Thank you.
Yeah.
Guys, we have time for one more question.
I think there was one question here.
Yeah, you were mentioning about like, there is, if a node goes down, then how the processing will happen. Can you please explain? And
Yeah. So when the node goes down, we have to make a distinction between why the node went down. Okay. So there are these signals that you get from operating system. Ray attempts to catch those signals and figure out whether it's a graceful termination or non-graceful termination. If it's a graceful termination, then you can actually configure. You'll get a grace period. You as a not as a user. So OS exposes this, and Ray is a client of OS. So Ray utilizes those things. So in that grace period, it will let the work drain, as in let it complete if it can. Maybe the work needs to process 1,000 partitions. It will just process 500 in the grace period that is remaining. And then 500 of those partitions will be streamed to the while partition 2 is being processed. Partition 1 would, the output of that would be written to the disk. So all of this work is pipelined. You don't want those 500 to wait till 500 partitions are processed. So that's the good case of termination. Non-graceful termination, you have no control basically. So checkpointing and backed by all the metadata, you back it by a highly available Redis cluster. We didn't talk about the head node much, but head node can be backed by a Redis cluster. This is not in memory, totally in memory of the head node itself. So the checkpoints are persisted, and whenever the job starts, or rather the task starts again, Ray head node knows any particular stage, any particular task, up to what checkpoint that was processed, and is able to. So if something has been checkpointed, then its output is persisted somewhere. That's the meaning of checkpoint. So it knows from where to pick up again and will start processing. That will incur slightly higher cost than the than the graceful termination scenario. Yeah.
but how are we guaranteeing like we are not losing anything in terms of data?
Checkpoint.
Yeah.
Yeah.
So checkpoint, like while we are processing, like any best practices to follow so that like we are not losing upon any data over there while processing. How can we guarantee that?
So guarantee in the sense there are formal correctness invariants that is part of the scheduling workflow itself. So those invariants are baked into the code. We can talk about what those invariants are. But basically, whenever we start reprocessing after a failure, right, those invariants ensure that you are not processing something which is not required to be, and also you are not missing which should be processed. You're getting it right. So no extra processing. Something that has already been processed should not be processed, and don't miss anything that is not yet processed. And internal mechanism, I can talk after the talk.
Thank you.
After this.